will give you a short introduction of what we do, but basically also want to give you kind of 3 takeaways when we talk about building companies or businesses around AI and what our key learnings are besides this. If you want to know more about what we do, feel free to approach me afterwards and we can have more talk about that. So a little bit about our company. So we are something about over 50 employees now. Like, it's all about the people. That's why I always like to say this the first thing, because this is the most important thing to us. As Jasper said, we've managed to get some significant investment, over $50 million, amongst which NEA out of the US. We have some VC fund out of Munich. We also have Alibaba now more recently as a strategic on board. And we are working across Europe so far. So we're working in Germany, Sweden, France, but also expanding slowly into Japan, China, US. So other sides of the world, bringing our technology there, right? In our space, it takes a bit more longer. It's a bit more complex because we have regulations and so on and so forth, but I will tell you about that in a minute. Now, what is our mission, right? And we spent a lot of time thinking about this at the beginning of our company, and we said, okay, the goal is to empower the railway system to operate with the highest availability, right? So that means everything needs to be on time, all maintenance is scheduled accordingly, all the things work as they should, because the railway is here to serve us, the people, right? We need to go from A to B, so the railway needs to empower that. And we want to empower them to be able to do that. Now, why railway? Yeah. Pretty simple. If you look at a number of different reasons for it, right? If you look at emissions, if you look at accidents, if you look at noise, if you look at impact on climate change, like railway beats all other modes of transport, right? Doesn't matter if it's personal or if it's freight. Railway is kind of the safest, the most efficient in terms of energy, the most climate friendly. So basically, in our view, as the generation who is kind of trying to save the planet, right? We were thinking that the railway is the one thing we want to support the most because it gives back the most to the planet. Now, the problem with railway, though, today is that you have something like, in Germany alone, 12 million passengers traveling every day, and there's 1 in every 5 passengers who is experiencing a delay which is higher than 6 minutes, right? And I think everyone in this room can say they were almost once delayed with a train. So that's, unfortunately, still a big problem. And at the same time, we have half of the passengers traveling which are dissatisfied with the service, right? So I don't want to tell you what's the customer satisfaction grade that the Deutsche Bahn has, because it can be gravely improved, right? But this is the proof that, okay, there's something needs to be done, right? Things need to change. And another thing about railway is that, as with many industries which are very traditional, right, which have been here for a long, long time, there's a lot of rules and protocols which have been designed in the 70s, in the 60s, that describe how work should be done, that describe how certain decisions should be taken. And the problem is that those things don't rely anymore to what's happening today, right? You have doubled the number of trains running on the track. You have doubled the load of cargo trains running on the track. You cannot do maintenance the same way, right? It doesn't work like that. At one point, you will reach a point where you're not being able to serve with the maintenance you're doing to ensure the availability that you need for a network. So how to go about it, right? Because it's a big problem. It has a huge impact, but you can assume it's not easy to solve, right? So the first thing that we learned when we started Konux and when we were starting to solve this challenge was that it's all comes down to 3 different things, right? Of course, number 1, you need to have the domain expertise. So as we heard about AI today and talked about it, I think it's clear that understanding the system you're trying to predict, you're trying to modulate, you're trying to analyze, gives you a lot of edge, right? And understanding what the input and the output is, for example, helps you create a better algorithm. So the domain expertise is key for us. And then secondly, you need to pair that, in our case, with IoT, right? Because we're talking about a network which is across Germany, and there isn't any system out there designed to send us data, right? So all of the data that is being aggregated so far today is by systems that are being designed maybe, let's say, 20 years ago, and those were designed for process control, not for data, for analysis. So this 2 different things, right? I'm an electrical engineer of my background, so I can tell you when we talk about process control, it's much more about, okay, real-time information, being able to take the decision. When we talk about data analysis, we need much more deeper level of data depth, but also much more precise information on specific points. And third, of course, AI, right? Because this is one of the problems where not having information out there makes it difficult for you to think about, okay, how can I solve it, right? Just taking a simple example, we are focusing on railway switches, right? And the railway switch is a point where the railway is changing on the route from one track to the other. It's very simple physical systems. If you look at it, it has some metal points, some concrete components, and then there's a train running over it, and that's it, right? But the problem is that it can be influenced by so many variables like the weather, how was it installed, what speed the train is running, what weight the train has, how was the metal processed, and so on and so forth. There's a lot of different variables which data you don't have. You don't know because this happened maybe 20, 35 years ago when the switch was installed. So what you need to do is you need to create some system that is able to react with an intelligent algorithm based on a small amount of data, but then you add a lot of domain expertise to kind of make it more powerful, right? So we call it small data, which is kind of big data in disguise, right? Because you don't have all the information you need, but you need to make some decisions. Now, second thing that we learned also in our process of working in the space is that ideally you manage to place yourself in a strategic data acquisition cycle. And what I mean by that is something that we didn't invent. So this is something we learned from the likes of Andrew Ng. If you know him, he's one of the most known people in AI. He led the Google AI team. He led the Baidu AI teams. And he said to think about it the following, right? At first, you want to create some data. You want to have some data gathered in the field, right? So in our case, we want to have some acceleration measurements of some trains pressing the switch. Based on the data, you build a product, you build a service that gets immediate value to your customer, right? So something that he can use to change something he does immediately. Not something where he needs to wait first 1 year for the business case to realize, but something he can use immediately. By doing that, you convince him to give it to more and more users. And when the users start to use the product even more and more, you gain traction for more data, right? So it brings you back into the cycle. For us, for example, we installed acceleration sensors. We give them information about when the switch is going to fail. They come back to us and say, okay, we also have this maintenance history, and we also have this type of electrical sensor data, which we look at other components. What can you say about that, right? And it puts us in this strategic data acquisition cycle where we constantly get more data, build better products, bring more users to the product, right? And in this case, you kind of create something which is very defensible because only you have the learning with the data, but at the same time, you're very focused on delivering customer value in a short period of time. This is very, very important to us, and I can recommend you, there's even a talk online by, just Google Andrew NG, and I think it's one of his main things on YouTube, and he explained this also in his words, and I think this is one of the key things when we talk about AI, to be aware that you need to create your own data acquisition strategy framework, and basically based on that, deliver valuable products for customers and drive more and more users to those products. Now, in our case, we have a device, right, which looks like this. We don't manufacture it ourselves. We have partners that do that for us. We just own the design of it and the whole IP around it. And it's something we attach to the rail track, right? So in this situation, you see it next to the blade. Making it a bit more complicated, the switch has more components. One of it is a blade. These are the sleepers, right? And then we install the sensor there. The train runs over it. And then what you get is something like this, right? So what you see here is an ICE. An ICE passes the sensor, creates an acceleration trace, and then out of the acceleration trace, we can convert it in so-called vertical displacement, so that how much the track is moving up and down when the train is passing over. And that is information we take to look at the condition of the ballast. The condition of the ballast is how fixed are the stones that are sitting underneath the switch, right? Data has shown us that if you have a good ballast condition, the number of failure that you see at a switch reduces by a factor of 6. So basically, the first conclusion was, okay, let's ensure that we always have a good ballast quality. In this case, we ensure that we have a low probability of having failures, right? And there's much more complexity behind that on how failures kind of relate to each other and how they can influence each other. But this is kind of the basic, simple sentence. And then we take this parameter or indicator and then apply some predictive algorithms to see how it's going to evolve in the future. Of course, it's not really a linear prediction, but you can approximate it to different ways, and then you can see, okay, when in the future do you need to fix the asset? A number of things I want to say here. And number one is that it looks as a very simple problem to solve, right? You have an acceleration sensor, you make it vertical displacement, so it's just like double integrating it, right, as we know from physics, and then you do some prediction, but come on, it doesn't look that complicated. The thing is that, as with all situations like this, the devil lies in the detail. And if you think about just converting acceleration into vertical displacement, into movement, if you have worked with acceleration sensors, the challenge there is that you always have a residual noise in there, and this causes your signal to drift, right? And even if this noise is very small, once you double integrate, it drifts a lot, right? So what we did here is we trained, I don't know exactly which type of neural network it was, I have to be honest, but a relatively small one, right? Because we need to be careful in terms of how well we can control the quality output of the algorithm, to just recognize, okay, where is the zero crossing, right? Because the zero crossing gives us an indication that where we can recalibrate the acceleration signal. It enables us to bring the drift back. And by recognizing that in the acceleration trace, we were able to set some reference points in the vertical displacement, and then create this curve, which is very, very, we've had to compare it with laser measurements, right, which do exactly the direct measurement of displacement, and the difference is 0.1 millimeter, right? So like the closest you can get to it. But basically, the point I was trying to make is that we take an AI component and we place it somewhere in our processing pipeline where we need it, right? So we don't have the data to afford to go into deep learning because no one has seen this type of information before, right? There's no historic data. We cannot compare it to anything. There's no patterns we can look for. But we need to think of, okay, which of the things that we need to solve in our algorithm can we solve with small AI components? Like right now, what we're doing is we're taking the acceleration trace, and we're detecting based on it which type of train is it, right? So we can give you, in theory, actually also in practice, we can give you a full train schedule over a switch after 1 day. We can say, okay, this was an IC1, that was an IC2, that was an IC4, that was a regional train, that was a cargo train. Because if you look at acceleration traces, there's certain patterns in there which give you an indication what type of train it is. Again, for that, we use, at the beginning, we started using something like, let's say, a very simple, how to call it, like, imagine it as a vector, right, which describes the characteristics of a train, which is kind of the distance between the axles, the ratios between the axles, so on and so forth. And we just place that vector into a space. And then every new train was a new vector, right? And the closer it was to a specific type of vector, it was a specific type of train. Like, this was the beginning way of doing it. Then afterwards, we moved into more often, let's say, again, neural network type of training because we had more information of the actual schedule. We knew exactly what type of train was running over it, and it was easier for us to train and say, okay, if this is happening, this is what type of train you're going to see. So coming back to my initial point is we are always the fans of saying, okay, we don't want to just apply AI generic. We want to look at specific components of our product and where can it be beneficial for us. And then, of course, it's important to be able to predict in the future. There's a couple of key metrics, right? Specific components need a specific time so that you are able to react, but that the customer is able to react, right? Because it doesn't matter if I tell you, okay, this is going to fail in 5 days, if you're not able to react anymore. And when we talk about ballast condition, a huge, let's call it mini train, has to come out, has to temple the whole track needs to be closed. So there's a lot of lead processes which have to happen before the failure can be solved. So there we need at least 90 days prediction horizon so that they can plan ahead if something gets detected. At the same time, we need a relatively high hit rate for something which hasn't been done before because the data was not there. Again, because our customers cannot afford to just run a train of that on the track. It impacts availability for them, so it causes delay minutes. It costs a lot of money. Like a tamping measure costs 80 to 100,000 euros just running this tamping train out of it. And then they have to be sure that when they do it, it makes sense, right? Because if not, they're just creating a lot of additional cost due to false positives that our algorithm is delivering. And 90% is just the beginning. Now we're somewhere at above 95%, which we have to deliver towards them so that they can guarantee the availability of the track. So basically, at the end, what are we trying to do? We're trying to make trains be more punctual. Why is that relevant with the switches? Because the switches cause 20% of all delays. So like 1/5 of all delay minutes is caused by switches. And this is something with, if you manage to solve that, you make the trains more punctual. Secondly, we want to have assets that last longer, right? Because most of them get replaced based on cycles. And knowing when a component has reached the, let's say, end of life or a place in its lifetime where it's not usable anymore should be also driven by data, right? Not just purely by cycles. And third, we want to make maintenance more efficient. So one of the things which I don't have on the slides right now, but what we've seen also was there was a specific curve of degradation, right, of things happening. And then we recommended the customer to do a specific type of maintenance. So he went out, did the maintenance, he came back, realized, okay, nothing changed, right? Then we recommended it again. He went out, did it again, came back, nothing changed. So we could validate kind of in a matter of, let's say, 2 to 3 weeks, 5 different maintenance measures to see which is the most effective one. Before us, our customers did a maintenance, waited 6 months to see what happened, and after 6 months, okay, they realized, okay, they have to do it again. But in that 6 months, the degradation of the asset just increased and increased and increased because the maintenance that was done initially was not the right one. And we're giving them the option to validate maintenance measure because we also have to learn, right, which are the most effective ones. But we give them the option to do that in a very short period of time. They can iterate, they can improve, and then they can decide what's the most effective. So basically, as we put it always into the voice of our customers, predictive maintenance will help us intervene at the right place of time, at the right place, at the right time, and with the right method. Yeah. Thank you.
And you guys know that Deutsche Bahn has just said that they want to improve the punctuality a lot.
Yes.
So I guess that's only because of you guys.
we hope to be a big part of that.
Okay. I think we're all looking forward to that. Any questions from the audience?
Oh, it's very hot.
You're all flashed away. I would have one.
Yes.
So I think we had a similar one before. So obviously you have to get the data, and then you get some prediction out of the data, and then you have to test it, and you just said it. How does it work with such a project? I mean, I would assume you don't roll it out entirely across the whole tracks. So how do you go step by step? What do you prove? And
so we, for example, what we did at the beginning, we took the whole, the customers like the Deutsche Bahn, they have a history of failures, right? It's just a history of the asset and what happened to this asset and what type of maintenance they done. Now, I'd not argue it if it's accurate or not, but it's there. So we took that and looked at, okay, what are the most common types of failures? How frequently do they occur? And what type of switches do they cover, right? So this gave us an indication when we look at the assets that we want to equip, how much do we need for how long period of time to be able to see specific failure types. So then we went back and said, okay, this is the number of assets that we want to have, and this is the period of time that we recommend for a project to be able to see something in the data, right? What happened afterwards was that actually you figure out that these things fail more often than the previous data showed, right? So we were able to see even in shorter period of time specific failures occurring, which we were expecting maybe to happen only 6 months later. So then when we came back to the customer and said, okay, we see this, this, and this. And he was like, okay, we haven't even thought about that. Like, why is this happening now? And then by that, we get into a cycle where every time something is happening, they call us and say, okay, so we've been out there, this is what we saw, what do you see in the data? And then we go back and check because we might have anomalies which we don't know what they are. Every time we see something, we go back to them and say, okay, this is what we see in the data, can you please validate for us, right? And I think once you've established that cycle with the customer, learning becomes more easy, right? Because before that, it's all about he said, she said, and then it makes it complicated to decide.
And just following up on that, I was wondering if you might replace yourself somehow, because since you are preventing all those failures, you miss the data in the future of those failures happening, so you can't challenge your models anymore, and then what happens? Have you thought about that, or am I just completely out of space here?
I think it's like the way there is like fairly long, right? Because you would have to ensure that all the maintenance is done 100% in time and 100% the right way and so on and so forth. And even that, then what happens is that by not having our system, you basically take your eyes out, right, if you remove it. And then even if you would like to do it, you don't know when you need to do it, right? Because you're not going to be able to adapt the cycles in a generic way that you fix all your problems. Because the situation is so dependent out there on temperature, how the train is running, like how the maintenance is being done, and all of these parameters which you cannot control, you will always need a set of eyes in the field to give you the information about that. And then secondly, for us, the maintenance is just the beginning, right? When we think about long term, we see ourselves as a type of operating system for the railway system, right? Giving them information not only about maintenance, but also understanding, okay, how does the train schedule, how is it evolving, right? What does make more sense to automate to gain more availability? What things should we look into when we talk about planning new routes, right? Planning new types of constructions. Right now we have a certain, today it's all driven by specific things that we want to achieve, like we want to have Deutschland stacked, right? So that's why we plan the routes in a certain way, but by having more data from the field, we'll inform that decision even better in the future. And there's a lot of data services we want to do on top of what we do today, but we need to get there, right? We need to get more data, more systems out there, and it's a step-by-step process.
Great. There's one question.
So as long as you can predict the suicide cycles, the first step, that's good. But the joker side, how do you monetize this at the end of the day? Short term and long term.
Yeah.
How do you make money with this?
So our current situation today is that we monetize it as we call it system as a service, right? So we have a per asset price, and then the contract itself is always a bit different, because these are customers who like to pay on a yearly basis, who like to pay maybe significant parts of money up front and so on and so forth. So I'm not going into that details, but basically the structure behind it, how we come down to the price, is looking at, okay, how much are we really saving? Like what's the impact of the solution? That's a proxy that we use to compute the price. And then we have a yearly paid fee per asset, right? So for every switch that we monitor, we get a yearly payment.
We have one more question in the back, and then I think we have to move on, but you will probably stay.
Connox for quite some time, and I'm really impressed by your development. If I see the numbers, you now raised, well, you have raised a bit more before, but something close to 50 million.
Yeah.
With 54 people. I know salaries in Munich are like hell, but what is your plan to utilize that money to grow in the exponential way to argue for such an investment, which is really incredible?
I think it's one thing that we've always tried for the beginning is that we wanted our investors to buy into our long-term vision, right? And our long-term vision isn't just, of course, we want to be a profitable company, we want to be completely sustainable, and that's all like big parts of what we want to do, but we also want to have a big impact on the railway industry. And it's obvious thing, and everyone knows by now, at least our investors a lot, that this is a thing with long cycles, right? It's one thing to get into a deal that takes like almost 2 years, but also changing a maintenance process. These are processes which have been there for 25 years, so all of these take a long time to change. So what we do, we say, okay, we need to be sure that we can manage this type of pace, right? We need to be sure that we don't end up in a situation where we need to raise money and there's also like all the deals almost being there. So what we do is say, okay, how can we be the most efficient with what our resources that we have, and how can we use it in the smartest way possible to get us there? So for example, we raised now the Series B, but before we raised the Series B, right, and even after we raised it until the end of last year, we haven't spent more money than we raised in our Series A. We kept everything under very close monitoring, making sure that we are delivering like all the milestones that we want to achieve, with the buffer that things might take longer, right? And in this case, if a tender like just goes from a timeline of 2 years to 4 years, for us that's like double or triple the runway, right? So we need to make sure that we have this capacity to really survive the change in the pace of the industry, and that's one of the key drivers in terms of financing. So like achieving the long-term vision, we need some fuel to be able to get there, but we need to be efficient about how we use that money.